All right, welcome back to IDIS 343. Now, over the last few parts, we built up the Q4 continuous review inventory system. You know, the one where we place an order quantity Q whenever the inventory position drops down to reorder point R. And we learned that the demand during the lead time is really the random piece that matters. Basically, we found Q and R by balancing holding, setup, and stockout costs. Well, today we tackle what happens when you can't really determine stockout cost. In this case, instead of a dollar penalty, we use a service level concept. We'll define two flavors, work the formulas, and run two examples. Now here's the picture. The jagged line is our inventory sliding down as customers buy, and when it touches the reorder point R, that dashed line, well, we place an order of size Q units. But, you know, the order doesn't show up instantly. It arrives after the lead time, basically the stretch labeled tau. And those colored dashed lines, they fan out to show different ways demand might unfold. That's like the whole question on the slide, right? What happens if demand follows one of these patterns? Notice all the uncertainty lives inside the lead time because that's the only stretch where we are exposed. Okay, same graph now with the answers filled in. If demand during the lead time is slow, well, inventory costs down and the order shows up while we've still got stock. That's, you know, the excess inventory case, the upper lines. But if demand runs high, inventory crashes through zero before the truck brings the next delivery here, and basically we stock out that steep line at the bottom. Now, the reorder point R is really just a buffer. Set it high, you almost never stock out, but you carry more. Set it low, you like flirt with shortages. Choosing R is basically choosing your service level. All right, we'll look at service levels for continuous review systems. And service, you know, in general just means the probability that a demand gets met, or when a customer arrives, we have the product available for them. Now, there are two service definitions. Type 1 service is basically the probability of not stocking out during the lead time. We call it alpha. And type 2 service is the proportion of demands actually filled from stock. The fill rate, we call that beta. Well, look at the 10 order cycles in the table. For type 1, we just count the cycles with no stock out. 8 out of 10, like 80%. For type 2, we add up all the demand and 1450 units. Subtract the 55 that's stocked out. That's 1395 over 1450, you know, about 96%. Same data, two really different numbers. Now, suppose there's a disruption and in cycles 3 and 6, we can't satisfy any of the demand, the 235 and the 200. So what changes? For type 1, well, nothing. We still had stockouts in those two cycles, you know, 8 out of 10, 80%. Type 1 only cares whether a cycle stocked out, not how big it was. But type 2, it basically collapses. Now 435 units stock out instead of 55, and the fill rate drops to 1450 minus 435 over 1450, like about 70%. And that's the book's key point, right? Type 1 can look perfectly fine, while service, as the customer actually feels it, just falls apart. All right, let's formalize type 1. Alpha is basically the probability of not stocking out in the lead time, and alpha completely determines R. Now, with type 1, R and Q decouple, you know, you can solve them independently. To find R, you set the cumulative distribution of lead time demand equal to alpha, that's F of R equals alpha, and read off the reorder point. Then, well, you just set Q equal to the EOQ from chapter 4. No iteration, no loop, like two clean steps. That's why the book calls type 1 very easy. The catch, which we'll see in a minute, it usually isn't, you know, what people mean by service. Now, type 2 is trickier because it ties R and Q together. Beta is the proportion of demands met from stock. And the average fraction that stocks out each cycle is N of R over Q, which means 1 minus beta equals N of R over Q. Basically, that gives N of R equals Q times 1 minus beta, you know, the expected units short in a cycle. Well, I mean, we approximate Q with the EOQ, and for normal demand, N of R equals sigma times L of Z, the standardized loss function. You set sigma L of Z equal to EOQ times 1 minus beta, solve for L of Z, look up Z, and finally R equals sigma Z plus M. More steps, but like the same toolkit, you know. All right, let's put it to work. Now, you remember Sophia runs a boutique called Taste of Europe, and she sells, a premium truffle-infused olive oil sourced from France. Each bottle costs her $15 and replenishment takes a year-long lead time. She uses a 20% annual interest rate for holding, estimates a $30 goodwill loss per stock out, and pays about $40 in admin per order. She expects to sell about 400 bottles a year, basically with a standard deviation of 60, and demand is normal. Okay, the question, what's the optimal Q, R policy if Sophia wants no stockouts in 90% of the cycles? Well, type 1 service at 90%. Okay, here's the work. The annual demand rate lambda is 400. Holding cost H equals IC, 0.2 times 15, which is, $3. The penalty P is 30 and the setup K is 40. Now for type 1, we want F of R equals 0.9. And from the normal table, well, that's a Z value of 1.28. That gives R equals sigma Z plus mu, 60 times 1.28 plus 400, which rounds to 477. And the EOQ is the square root of 2 times 40 times 400 over 3, basically 103 units, our Q. The policy is QR equals 103,477, right? All right, same store, new question. Now we just locked in the type 1 policy, 103,477, to hit 90% of cycles with no stock out. But here's what a manager, really wants to know. With that same policy in place, basically, what type 2 service level, what fill rate are we actually delivering? I mean, of every 100 bottles a customer asks for, how many can Sophia hand over straight off the shelf? Well, let's compute it. Okay, we keep the same numbers. The EOQ is still 103 and the relationship is N of R equals sigma L of Z equals EOQ times 1 minus beta. Now R is 477, which came from Z equals 1.28, and the loss function L of 1.28 is, 0.0475. And that makes sigma L of Z 60 times 0.0475. Set it equal to 103 times 1 minus beta, and well, solve. Beta is 0.972, and there's the punchline. I mean, that 90% type 1 policy is basically quietly delivering 97.2% fill. Type 2 looks better, because partial fills still count. All right, second example. Now, David owns a bookstore and stocks a special edition novel for $20. And, restocking takes a year. He uses a 15% annual interest rate, estimates a $25 goodwill loss when the book's out of stock, and pays a $30 admin fee per order. He sells about 150 copies a year, basically with a standard deviation of 25, and demand is normal. Well, first question, type 1. What order quantity and reorder point prevents stockouts in 95% of his cycles, Okay, same method as before. Lambda is 150, holding cost H equals IC, 0.15 times 20, which is, $3. The penalty P is 25 and the setup K is 30. Now for 95% type 1, F of R equals 0.95, and the table, gives Z equals 1.65. That makes R equals sigma Z plus mu, 25 times 1.65 plus 150, which is 191.25, round to 191, And the EOQ is the square root of 2 times 30 times 150 over 3, basically 55 units, RQ. And the type 1 policy is 55, 191. All right, now we flip David to a fill rate target. Everything stays the same, same costs, same demand, same sigma, only the goal changes. Instead of 95% of cycles with no stock out, Well, David wants 95% type 2. Basically, he wants to actually fill 95% of the demand. Now, what order quantity and reorder point does that take? Like, watch how much the reorder point moves. Okay, lambda is still 150 and the EOQ is still 55. For type 2, n of r equals EOQ times 1 minus beta, 55 times 1 minus 0.95, which is, 2.75. Now, since n of r also equals sigma L of z, we've got 25 times L of z equals 2.75, which basically makes L of z 0.11. From the loss table, well, that's z equals 0.85. Then r equals sigma z plus mu, 25 times 0.85 plus 150, about 171. The type 2 policy is 55, 171. And notice R dropped from 191 to 171, like same 95% label, very different reorder point, right? One last twist. Now, suppose David instead ran the policy 55, 130. Same order quantity, but a much lower reorder point of 130. Well, before we grind the math, let's just reason it out. We just saw that 95% type 2 needed R around 171. And this new R, 130, is below that, even below the mean of 150. Now, would the fill rate come out smaller or larger than 95%? I mean, intuition says smaller and like a lot smaller. Let's confirm it. Okay, Q is still 55. We work backward from R equals 130. R equals sigma z plus mu means 25z plus 150 equals 130, which, gives equals negative 0.8, a negative z basically because R sits below the mean. And from the table, well, L of negative 0.8 is 0.9202. Then n of R equals sigma L of z, 25 times 0.9202. And that equals EOQ times 1 minus beta, 55 times 1 minus beta. Solving beta is 0.582, like about 58%. Just as we predicted, right? Way below 95. I mean, dropping R by 40 units cut the fill rate almost in half. That's how sensitive service is to the reorder point. All right, that's type 1 and type 2 service in Q, R systems. Thanks and gig 'em.